Imagine you are being hunted. The predator is right there, close enough to strike, and you cannot see it. Not because it is hiding, not because it is camouflaged, because it is shining a light directly on you and your eyes are physically incapable of detecting that wavelength. You are lit up, completely visible to the thing hunting you, and you have no idea. You are swimming through what your nervous system tells you is total darkness, while something watches you in full illumination and moves toward you. This is not a thought experiment. This is not a hypothetical. This is what happens right now in the deep ocean. Every night, a fish called the dragonfish has evolved the ability to produce red bioluminescence light at a wavelength that the vast majority of deep-sea animals cannot see. It hunts in a private visual channel, a spectrum of light completely invisible to its prey, and its prey swims through that light completely unaware it is already seen. This is one of the most sophisticated sensory systems ever documented in an animal, and most people have never heard of it. The dragonfish belong to the family Stomiidae, a family of deep-sea predatory fish that includes approximately 300 known species, among them the loosejaw fish, the viperfish, the hatchetfish, and the subject of this video, the dragonfish, particularly the genus Malacosteus and related genera, including Aristostomias and Pachystomias. These are the specific species that possess the extraordinary red light system we are going to examine in detail. Stomiidae as a family were first formally studied in the 19th century as deep-sea trawling expeditions began returning specimens from depths previously inaccessible to science. Early naturalists examining these specimens were struck by two things. First, the jaw structure. Many stomiid fish have jaws that appear physically too large for their bodies, hinged at the back of the skull, in a way that allows the mouth to open to angles that seem structurally impossible. Second, the photophores. These fish are covered in bioluminescent organs, rows of photophores along the belly, photophores behind the eyes, photophores on fin rays, a long chin barbel tip with a bioluminescent lure, sometimes itself complex enough to mimic small prey animals in both shape and light output. But it was not until the late 20th century, specifically research conducted in the 1980s and 1990s by marine biologists, including Edith Widder, then at the Harbor Branch Oceanographic Institution, that the full significance of the red light system was understood. Widder's research into deep-sea bioluminescence produced one of the most significant discoveries in marine biology of the late 20th century. The dragonfish was not just producing red light, it was producing red light that it could see, and that almost nothing else in the deep ocean could. A private visual channel, operating in plain sight, in the darkest environment on Earth. To understand why this is extraordinary, you need to understand what happens to light in water. Specifically, what happens to red light. Sunlight contains the full visible spectrum: violet, blue, green, yellow, orange, red. When sunlight enters the ocean water, it begins absorbing different wavelengths at different rates. Red light has the longest wavelength in the visible spectrum and is absorbed first. Within approximately 10 to 30 meters of the surface, depending on water clarity, essentially all red wavelengths are gone, absorbed by the water. Below 30 meters, red does not exist as a transmitted wavelength in the ocean. This creates a predictable, reliable consequence for deep-sea evolution. Any animal living below 30 meters that evolved red coloration got free camouflage. Not because red blends into the environment visually, but because red, in deep water, appears black. There is nothing to reflect, no red light to bounce off a red surface, so deep-sea shrimp are red. Deep-sea crabs are red. Many deep-sea fish have red pigmentation, not for display, not for communication, for invisibility. Red equals black at depth. This is established, well-documented marine optics. Now here is where the dragonfish changes everything. If red light does not exist at depth because water absorbs it all before it can penetrate, then no deep-sea animal ever needed to evolve eyes capable of seeing red. There was nothing to see, no red light to detect, no evolutionary pressure to develop the visual machinery to process it. So the deep sea evolved without red vision, comprehensively, almost universally. The deep ocean became a world where red as a visual experience simply did not exist, and the dragonfish found the gap. Here is what Edith Widder and subsequent researchers documented. The dragonfish, specifically Malacosteus niger and related species, possesses two things that almost nothing else in the deep ocean has. First, a photophore beneath each eye, capable of producing red bioluminescence, not blue-green like the vast majority of bioluminescent deep-sea organisms. Red, a wavelength of approximately 650 to 700 nanometers far into the red end of the visible spectrum. Second, a visual pigment in its own eyes capable of detecting that red light. This is the piece that makes the system complete. Most deep-sea fish have visual pigments tuned to blue-green wavelengths, the wavelengths that penetrate deepest in water, and that most bioluminescent organisms produce. The dragonfish has a modified visual system in certain species, achieved through a dietary mechanism involving chlorophyll derivatives from consumed copepods that accumulate in the retina and shift its sensitivity toward longer wavelengths. The dragonfish effectively upgrades its own vision by eating. The result is a predator that can produce light its prey cannot see and detect the reflections of that light with eyes specifically tuned to that wavelength. It illuminates the world in red. It sees that red world, and everything around it swimming through what their visual systems register as complete darkness is lit up. Visible, detectable, findable. The dragonfish hunts with a flashlight nobody else can see, in a room full of prey that do not know the light is on. The red light system alone would make the dragonfish remarkable, but it exists inside a body that is in its own right one of the more extreme designs in deep-sea biology. The dragonfish is typically between 15 and 40 centimeters in length, small by the standards of ocean predators. Its body is dark, almost black, with the kind of non-reflective pigmentation that absorbs any ambient light rather than scattering it. It is, in the visible spectrum available to most deep-sea animals, essentially invisible. Its jaw. The jaw of the dragonfish, particularly in the genus Malacosteus, is one of the most mechanically extreme jaw structures in the fish world. The lower jaw is loosely connected at the front, not rigidly fused the way most fish jaws are, and can drop dramatically below the body axis when the mouth is opened. Some species can open their mouths to angles exceeding 120 degrees relative to the body. The jaws are equipped with long, fang-like teeth, curved backward, that in some species are so long they cannot be contained within the closed mouth, and instead fold into sheaths inside the skull. Teeth too large for the head to hold. The entire jaw apparatus is designed for one purpose: capturing prey that cannot be allowed to escape. In the deep ocean, where a meal may come once a week or less, a missed strike is a potentially fatal energy expenditure. The dragonfish's jaw ensures that anything that enters the mouth does not leave. Then the barbel. Many dragonfish species have a long chin barbel, a filamentous appendage extending from the lower jaw that can reach lengths equal to or exceeding the body length of the fish. This barbel is tipped with bioluminescent tissue, in some species elaborate enough to mimic the appearance and movement of small crustaceans or fish. A lure. Dangling below the mouth. The dragonfish does not chase prey. It waits still, dark, invisible, while its barbel attracts prey into striking range. Combined with the red light system above, prey that is not lured from below can be hunted from above using invisible illumination. Two independent hunting mechanisms. In the same animal, the dragonfish's red light system has implications that extend beyond the individual animal. When Widder's research confirmed that certain deep-sea predators were using red bioluminescence and that certain prey species had developed the ability to detect it, it revealed something about the deep ocean that had not been previously understood. The visual ecology of the deep ocean is more complex than the simple binary of darkness and bioluminescence that earlier research suggested. There are multiple visual channels operating simultaneously in the deep ocean. Most animals communicate and hunt in the blue-green channel, the wavelengths that water transmits, and that most eyes can detect. A smaller number of predators, the dragonfish among them, operate in the red channel, invisible to most. And research has found that the evolutionary arms race does not end there. Certain prey species in habitats where dragonfish are common have developed some sensitivity to longer wavelengths, not full red vision, but a slight extension of their visual range in the red direction. An evolutionary response. Prey, over time, detecting the threat they could not previously see. The dragonfish is not unique in its environment. It is part of an ongoing invisible arms race, predator and prey each responding to the other's capabilities, playing out in complete darkness at 500 to 1,000 meters below the surface. An arms race in a visual channel most of the planet does not know exists. And here is the detail that puts this in perspective. We discovered this arms race in the 1980s and 1990s. It has been running in the dark for millions of years before we found it. How many other sensory arms races are operating in the deep ocean that we have not found yet? We genuinely do not know. Edith Widder deserves specific mention here. because the discovery of the Dragonfish red light system did not happen by accident. It happened because one marine biologist spent decades developing the tools and techniques needed to observe bioluminescence in the deep ocean without disturbing it. Standard submersible light's white light cause immediate behavioral responses in deep-sea animals. Everything scatters, everything hides. Widder developed the Eye in the Sea, a camera system using red light illumination that could observe deep-sea behavior without triggering flight responses. Because red light for most deep-sea animals is invisible, the camera was invisible to its subjects, and what it recorded changed marine biology. Animals that scatter when white light hits them behaving normally under red illumination. The dragonfish itself illuminating prey with its subocular photophores and footage that confirmed the theoretical model with direct observation. Widder went on to co-found ORCA, the Ocean Research and Conservation Association, and continued deep-sea optical research that has produced some of the most significant bioluminescence data in the field. The dragonfish story is not just about the fish. It is about the specific, difficult, patient work of science building the tools to see what is actually happening in a place that is almost impossible to reach, and finding, as so often happens in the deep ocean, something stranger than the hypotheses that went looking for it. The dragonfish is small, 15 to 40 centimeters, dark, slow-moving, patient. It lives in the mesopelagic and bathypelagic zones 200 to 1,000 meters below the surface in water that the vast majority of the planet will never see. And it has built through millions of years of evolutionary pressure, a sensory system with no equivalent in the sunlit world above, a light source that illuminates without revealing itself, an eye that sees a spectrum the world around it does not know exists, a jaw that cannot be escaped, a lure that mimics life, and a body so dark it absorbs the light it produces before that light can scatter and betray its position. It is a predator that operates in a dimension of reality that its prey cannot access. That is not metaphor. That is documented biology. And somewhere right now, at approximately 600 meters below the surface of an ocean, one is shining its invisible red light through dark water, watching, in a spectrum nobody else can see. Everything it needs visible, everything around it blind. If this is the content that keeps bringing you back here, subscribe, because there are so many more of these waiting. Every single one documented, every single one already happening, right now, in the dark. In wavelengths of light we are only just learning to find.